So in the first video, we are going to see an introduction to the PEB process environment block. So for that, we need to install the WinDBG. You can Google for the WinDBG install and you can download the WinDBG, or you can even install the Windows SDK and WDK. If you have already installed, you will get the debugging tools. You can go to C, program files x86 and Windows kits and 10. Here you will see the debuggers and go to the x64, and here down you can see the WinDBG. So I have pinned that to the taskbar. I'm going to right click on this and run as administrator. So I have a notepad process running, so I can attach to that process. So go to file, attach to a process and choose notepad.exe process. And click on OK. And now the process has been frozen. You cannot open the notepad. So you can type the command not peb to retrieve the peb information. So the process environment block contains the information about the process, the environment variables. So these are the environment variables, and these are the DLLs that our application is using, and also some other information like image base addresses, and is process being debugged. You can see the yes, because we have attached the WinDBG to the process. So you can also see the LDR. So from this LDR we have these modules, the DLLs. We are going to parse them in the future videos. So for now we can see the peb address here. So what you can do is you can do the command dt nt not underscore peb, and you can paste the address here to parse the contents at that address as a peb structure. So if you do not supply the address, you can just hit enter and you can see the members of the peb. So this peb is not directly documented in the Microsoft documentation. You can use the WinDBG and find the offsets of the fields. So this peb contains some valuable information for the user mode programs. So the first one is the being debugged. So you can see the one indicates that the process is being debugged. If it is 0, then that means no debugger has been attached to that process. And is protected process and image base address and LDR process parameters. So inside this process parameters you can have the current directory and the DLL path, image path name, the command line arguments that are supplied to the process, and the environment. Where is this environment? Oh, here it is. Here it is. It is a Unicode bytes, and here you can see the environment variables that are loaded into the process, etc. So this we are going to write the code that does not depend on any third party libraries. So we can fetch the peb address from our process itself. So we are going to create a DLL and inject the DLL into the process. So upon injection, the DLL function automatically retrieves the peb and goes to the LDR and searches for all the modules and find the kernel32 or user32.dll base addresses, and it will start parsing the exports like load library and get proc address, etc., and then loads appropriate other DLLs, and then we are going to parse the PE file as well. We are going to create a new memory, and then we are going to load all the PE, and then we are going to execute the DLL main. So this is just an introduction to the peb. So we are going to use this information to write our code inside our DLL that does not depend on the third party libraries. So that's all for this video about the basic introduction to the peb process environment block. So in this video we are going to retrieve the peb address from our C++ program. So let's go and create a new project. So open the Visual Studio and create a new project. and we need to choose the dynamic link library and click on next and name this as reflective loader. So here you can see the DLL main. So this is this gets invoked when the DLL gets loaded into a process, and these are the reasons. If the process has been attached, then the code under this case gets executed. If the process has been detached, the code under this branch gets executed. The same way for thread attach and thread detach. So what we are going to do is we are going to write a function as an export function. So we are going to talk about the imports and exports later in this course. So for now, bear with me and type this code extern C and decal spec DLL export and void text test. So this is the function we are going to export. So I'm going to use a program called PE Bear. It is a PE parser. It parses the PE file, exe files, and gives you the information. So what I'm going to do is open this project folder and go to x64, change this to release and build the solution again. And inside the release, you will see the reflective loader.dll. So I'm going to open this file inside this PE Bear. So here you can see the reflective loader.dll, and we have exports and imports. So inside the exports, you can see the test function that is being exported. We are going to pass this extern C __ decal spec DLL export. So build this project again, and inside the PE Bear you can see the notification stating that file has been changed. Do you want to reload? Yes. And go to exports. You can see the two functions that are being exported, DLL main and test. So if you go and delete this one, so build this and reload, you will not see the test function. So you need to specify this DLL export so that our function gets exported. Okay, now we are going to create a new file, that is the header file. We can call this as helpers.h. So we are going to include the windows.h header file for the definitions, and also we are going to create an inline function. So we are going to say force inline. So what this inline does is, let me first write the function void. So u long, we are going to return the peb address, that is 64-bit, get peb address. So what inline does is, whatever the code you write inside this function, it gets directly replaced where you call this function. So suppose include helpers.h, I am going to call the get peb address. So normally when you call the function stack gets set up and the code jumps to the function address and gets returned back. But for the force inline, what you are going to do is the function code gets substituted at this point as it is. Suppose I write return a plus b, it takes int a comma int b, and get peb address int a comma 5,6. So instead of calling the function, the return code a plus b gets substituted. So this gets replaced by a plus b. That means 5 plus 6 directly without calling the function and executing that. So that is the advantage of force inline. And this force inline can depend on third party libraries, but here we are writing a position independent code that does not depend on any third party libraries or any hard coded addresses, etc. We are going to retrieve everything dynamically. So let's remove this. So remove this one. And what you can do is you can create a new project, create new console app, loader test, something like that. So inside the DLL you cannot print out the statements. What you can do is you can just create a new dummy program and write exactly the code what you are writing inside your main reflective loader.dll project. So okay, let's get the peb address. We are going to read the GS register. So inside the GS register you will have the thread specific information. So at the GS register at the offset 0x60 offset of GS register contains peb address. So there is a macro read GS keyword and specify the offset. So this gives you the 64 bit value, that is the peb address. So you can even use the assembly language to load the peb address. So you can add an existing you can create a myasm.asm and create a procedure get peb end p and then end. So move rax comma gs 60h and then return. So this code gives you the peb address. Since we have this intrinsic function, you can directly execute this one. So this will not do any position dependent. So it is position independent. So we are not going to use the assembly code for this. So u long peb address. So you cannot print inside the dealer. What you can do is you can go and copy the code here, include the helpers function, peb address. So in fact you can develop a loader inside your normal C++ project and then copy paste inside the DLL after you have completed the code. And you can see this is the peb address. So that's all for this video. In this video we have created a DLL and also a C++ project, and we have used the read gs keyword intrinsic function to read the peb address. Hello everyone, in this video we are going to see how to retrieve the process image base address. We have already seen this inside the peb. You have this image base address at the hexadecimal 10 offset. So this image base address might not be useful for reflective loading. So this image base address is useful for DLL hooking if you want to do user mode DLL hooking. So in that case this image base address plays an important role. But anyway, we are going to retrieve this image base address as well. In the previous video we have retrieved the peb address. So we are going to write another function force inline u long long get process base address and u long long peb is equals to read gs keyword, and inside the peb you have the inside the peb variable you have the address, and from here onwards you are going to read the 8 bytes from the hexadecimal 10 offset. So from here onwards you are going to do the pointer arithmetic. So peb plus 0x10, so that is the offset here. So you want to read 8 bytes. So if you want to read 8 bytes, cast this value as u long long star and then do the dereference operator. So that gives you the u long long process base address. And here you can do the char star if you want to do the single byte pointer arithmetic. So otherwise uh, in C++, if you have a pointer to some 4 byte value, int a is equals to say 4 and int star p is equals to a, so ampersand a. So if you increment p plus plus, the p gets incremented by 4 bytes because it is pointing to an integer. So otherwise if you are going to do char star p plus plus, then it is going to increment by 1. So that is the difference you need to know. So that's why most pointer arithmetic, if you want to do a single byte pointer arithmetic, you must do this casting char star. So return process base address. So this we are inside our C++ program, so we can check this process base get process base address. So let's go and run this. So before that we are going to halt our program. So I'm going to ask the user input to input a number. So that is not necessary, we are just verifying if the process base is correct or not. So let's run this. So our program will be in a waiting state for the user input, so that we can verify the process base address we have fetched is correct or not. So I'm going to open the system informer, so run the loader test. So if you go and click on this loader test function, so loader test process, you have this process base, and here you can see the our loader test.exe, that is the process, and the base address is 389,000. So 389,000, you can see here the sections of the PE file. So that means we are retrieving the peb address correctly and also the process image base address correctly. So that means we are on the track up to this point. So that's all for this video. In this video we have used the peb address and read the 8 bytes at the 10 offset, so to get the image base address. So in this video we are going to see how to retrieve the DLL base address. So when the process has been loaded, few DLLs will automatically get loaded, like NT DLL, kernel 32 DLL and the kernel base.dll, and also other DLLs the process is importing. So this LDR structure, the peb LDR data contains the list of all the DLLs that has been loaded. So the LDR is at the offset hexadecimal 18. So if you click on this, this is of type peb LDR data. So what you can do is you can just click on this, or you copy this address and do dt peb LDR data, So here you can see the length and the inload order module list, in memory order module list, and in initialization order module list. So these three lists contain the same information but in a different order. So inload order, so this list contains the DLLs that are loaded first to the last. So the first DLL has been loaded first and the second DLL has been loaded second, and so on. In memory order module list indicates the memory addresses from the ascending to the descending increasing order. And in initialization order module, so which modules has been initialized first in the uh, ascending order. So we are going to use the inload order module list. You can use any of these list as well. So for example, if you click on this inload order module list, so you will get the list entry, so that contains the forward ring and the backward ring. So this is called a double linked list. So you have a forward and the backward ring. So this address points to the LDR data table entry. So that is the entry of the DLL, DTNT LDR data table entry, and paste the address, and you can see the image, that is the notepad.exe, and the full DLL name, the path of this binary. So you have moved towards the first image, that is the DLL. And next you can also see the first three members are inload order rings. If you click on this, you will get the forward ring, and you can do the same for this address as well. Parse the contents as a LDR data table entry, and you will get the next DLL, that is DLL, NT DLL. In the same way, you can do the same as well for the next as well. So in this way, you can loop through all the double linked list and retrieve the NT DLL, and also the DLL base address and the entry point and the size of image, etc. And one thing you need to keep in mind is that if you are following the in-memory order module list, so there is an offset. So if you go see the offset in memory order rings, so this address points to the in-memory order ring of the next DLL. So that means this one. So if you parse the contents as a LDR data table entry, you need to subtract this offset, because the address is pointing to the in-memory order rings, and you need to subtract hexadecimal 10 to get to the base address of this LDR data table entry. So for example, I can copy this and paste directly without subtracting. You will get the wrong values. So here you can see the base DLL name has been something garbage. So that's why you are going to subtract the offset of the 10, because that is the in-memory order ring. So now you will get the correct values. So that's why to clear the confusion, we are usually go with the inload order rings, because you don't need to subtract any offset. The base address it is pointing is the LDR data table entry. And what is the breaking point is the last one. So if you go to the DTNT LDR data table entry and paste the last link, the last one, and this is the DLL, and you can go to the inload order rings, and the F link of the LDR data table entry points to this address. So what is this address is this one. Sorry, where is the peb address? So the address of this list entry that is inside the peb. Let's do the peb. So if you click on this, so this address, so the LDR address 8C0 plus 10, that gives you the last module's F-link address. So 8C0 plus 10, keep that in mind. Now we are going top, and you can see here 8C0 plus 10 gives you the 8D0, which is exactly the address of this in this value inside the LDR structure. So that means the last module points to this address. So that is our breaking point. Until then, we are going to loop over the DLLs and print the DLL names and the base addresses. I have drawn a small diagram for a better understanding. So this is LDR data table entry, and in load order F link, it has a forward link and backward link, and same way you go through all the DLLs and get to the first point. So okay, let's write the function. So let's go and write our function force inline. It returns u long get DLL base address. So for now we are going to print all the DLL names. So by default we are going to return 0. So first we are going to fetch the peb address. So we can call this as ppeb, which is a pointer to peb. So we are going to read the 8 bytes at the offset of 18. So that gives you the LDR. So u long LDR is equals to char star ppeb plus 0x18. So we are adding the 18 bytes to get this point and parsing this as a u long pointer and dereferencing the contents. So this will read the 8 bytes. So we have LDR, and from this LDR we are going to read the 8 bytes at this 10 offset to get the first table entry. So u long first table entry is equals to char star LDR plus 0x10. So we have read this 8 bytes, and what we are going to do is we are going to say while true, if or we can do like this, while first table entry not is equals to LDR plus 0x10. So this is the breaking point we have seen. So the forward link, if it is pointing to the LDR plus 10 offset, that means that is the last module. So it's better to put at here after processing the first DLL. So while true, we are going to process the first DLL and then check if the first table entry is 0x LDR plus 10, then that means we are going to break. So now at this address we have the LDR data table entry, and at the offset of 58 you have the base DLL name. So the first table entry plus 0x58, and if you add plus 8 you will have the buffer address plus 8. U long base DLL name is equals to. So we have the buffer. You can see this is the address. What you can do is you can WC out dealer name, base dealer name, std handle. And we are going to advance the first table entry is equals to, so how do you advance is you read the first 8 bytes at the LDR data table entry, that is the this inload order module link and the f ring. So you can just cast this one, char star first table entry. So we are reading the 8 bytes at the starting address, that gives you the f ring, and we are assigning to the first table entry. So I hope we can print this one. So let's go and run this. So we have printed all the dealer names. So you can see the dealer name loadertest.exe and these other dealers. So my guess is we are missing one dealer because uh, while true, so we got the error. So I think this is good to go. So we have printed the dealer names. So what we need is the dealer base address. So at the 0x30, so u long dealer base is equals to 0x30. So copy this and 30. So we are reading the bytes, 8 bytes at the 0x30, that gives you the dealer base address. Dealer base address std hex dealer base std handle. Now let's go and run this, and we should see all the dealer names and their base addresses. So in the next video, we are going to write the string comparison function to compare to which DLL base address we need. So if you want to the DLL base address of the kernel 32, we are going to fetch only that one, not everything. So in the next video, we are going to see how to implement our own string comparison function that does not use external libraries. So in this video, we are going to see how to implement our own string comparison function. We should not use the standard string library, and also we should not use the print statements to print something, because we are writing the position independent code. It should execute without any dependencies. So we are writing a basic string comparison. So force inline bool, it returns a true or false whether those strings are equal or not, my strcmp. So it takes two parameters, constant char1 pointer, constant char star char2 pointer. So it will take a pointer to the characters for the string 1 and the string 2. So this here is a small diagram. Char1 pointer points to the string of bytes a b c d e 0, so this is the 0, and char2 pointer a b c d f. So the char1 pointer is initially at position a, and the char2 pointer is also at a. So while we are going to check if the char1 pointer is pointing to null byte or not, in the same way char2 pointer is pointing to null byte or not. So null byte is the stopping point for for our string comparison. So while dereference the char1 ptr and star char2 ptr. So what this does is this check whether the both values, both bytes are not 0. If they are 0, we are going to get outside the loop. So here we are going to return true, just a placeholder for now. So while these two bytes are not is equals to 0, we are going to compare these two bytes. So we are going to create a two new variables, char1 is equals to star char1 ptr, char2 is equals to char2 ptr. So we are dereferencing the byte at this address and storing that value in the char1, char2. So the char1 points to A and char2 is A. We are going to check if these are equal. So if these are equal, it's okay. We are going to continue the loop. Otherwise, if char1 not is equals to char2, then we are directly returning false. We no need to check other bytes, because if one byte is false, then that means these two strings are different. And at the end, we are going to increment the pointers. So this char1 pointer moves to this B, and similarly the char2 pointer moves to B. And we are storing the values inside the char1, char2, the values of BB, and checking if these are not equal, we are returning false. Otherwise, we are forwarding the char1 pointer and the char2 pointer. So at this point, we have moved to this ending E and F. So E and F are not equal, so we are returning false. So let's suppose A, B, C, D, E, and we have the G and S at this. So one bug in our code is if you face A, B, C, D, E and A, B, C, D is 0, then this function returns true, because we have reached the char1 pointer as null byte and the char2 pointer as G byte. So we are returning true in this case. We are coming out of this loop because of char1 pointer being null byte. So that's why we are returning true. So here we need to check another thing. If star char1 pointer is equals to 0 and star char2 pointer is equals to 0, then only return true. So that means we are comparing the both bytes being the null byte, then only return true, otherwise return false. Since here the 0 and G are not equal, so the G is not a null byte, so we are returning this loop does not get executed. This branch, we are returning false. So here we are comparing the normal bytes. So our code compares only the char normal bytes, the char star. Here we have the DLL names as a W char T. You can see here. So these are the 2 bytes. So these are the Unicode bytes. If you do the DB, and you can see the notepad.exe, every alternate byte is a normal byte and the remaining byte is 0. So what you can do is you can just copy this code and paste it here and just change this pointer to wchar underscore t, and the remaining all of this code is same. So this way you can compare two strings that are of character pointer, and also the two strings where one of the string is wide character. So you can delete this one. So we are going to use the templates. So the templates are very useful for writing the placeholder. So we have the two functions here. There is only one difference, that is the parameter. So what you can do is you can implement a template. So I'm going to call this. So the templates are fine. we can use templates in your reflective loader because they just do the substitution. I think in Java it does much more than substitution. So in C++, it will the code will be substituted. So that's why we can use template type name t comma type name u. So we are choosing the two types t and u, and the first parameter can be of type t star, a pointer to the t type, and also the second parameter can be a pointer to the u type. So while dereferencing, obviously we will pass the char star and wchar underscore t, and after that we are resolving, we are dereferencing the contents and storing it in the char1 char2. If they are not equal, we are returning false, and we are incrementing the pointers. So the thing is, it is very easy because the pointer increment does the increment of the u type. So here if you cached this address as a wchar t wchar underscore t star, so it will automatically dereference these 2 bytes as a single byte, so you will get the n value inside the character 2. Otherwise you have to loop through the alternate bytes and check the contents. So that is very not feasible, and we are automatically checking if the dereferencing the contents. So you dereference the 2 bytes and check if it is a null, then return uh, true, otherwise false. So I can go ahead and delete this one. So my code, my our simple str comparison is ready. We are going to check this. So let's say we want the DLL base address of the kernel 32.dll. So here, so if my strcmp, so the function takes should take constant char star dealer name to find. So my strcmp of dealer name to find and base dealer name. So we need to pass in the types. So the first type is character star and the second type is wchar underscore t. So if our strings are equal, then we can print the DLL base address. So pass in the kernel 32.dll. So if you go and run this, okay, kernel 32.dll, the name should be, let's call this as notepad.exe. So we did not implement the lower case and uppercase. So we need to input the string exactly. So somewhere there was a wrong. So we have got the address for the ntdll base address. Let's check for other DLL. So kernel 32.0, so it's all the capital uh, alphabets. So that's why we did not get the DLL base address before. So let's run this and you should see the DLL base address. So that's why we need to implement the lowercase comparison now. So in lowercase uppercase to lowercase c. So I always forget this. So if the character is in between the A and Z, we need to add 32. So it's a ASCII table. So these are 32 numbers apart. So that's why we can just copy this and paste here. So if char1 is in between the A and Z, char1 plus is equals to 32. So do the same for the char2. So we are retrieving the character and checking if it is in between A and Z. We are adding plus 32 to convert it into lowercase. And now let's change this to kernel32.dll. Now we should get the same address. And you can see we got the address. So you can do like this, ntdll, and we got the address. So that's how we can implement our own string comparison. Very simple function to immediately to quickly test two strings are equal or not based on those pointers. Also one more thing, you should not use this one. You should not use a constant char star in your program in the reflective loader DLL because this gets stored in the data section. So that's why we are going to create an array, character kernel 32 array. So you need to define each and every byte, kernel 32 dot DLL, and the last one is 0. So now pass in the kernel 32, you should get the same address. Okay, so this array will be stored on the stack instead of data section. So that's how you can create a position independent code without depending on the other sections. So that's all for this video. In this video we have written our own string comparison function and used it to identify the particular DLL base address. So in this video we are going to talk about the PE file format, just an introduction. In the next video we are going to write the code how to parse the contents. So the file format exe, DLLs, driver files .sys and the control panel applets all come under the PE file format. Even the firmware uh, the .efl file also come under the PE file format. So it is also an exe. So it is very important to learn about the PE file format for reflective loading. So if you go to our project, go to the binary loader test.exe and go to this website hexedit.it. This is an hex editor, online hex editor. You can go and throw this binary at here and you can see some contents here. The starting 2 bytes indicates MZ, the architect of this PE file format. You can see the ASCII MZ. So this MZ, if you see the MZ, so this can be a PE file format. So this is called signature for the PE file format. If you open any of the PE file format, you will see the first 2 bytes MZ. And also the first 64 bytes contribute to the DOS header. So we will see the headers in the next videos. So the first 64 bytes are the DOS header, and the following you will have the rich header. There is an offset in the DOS header that points to the file header. This 01000 0100. So if you go to 0100 and you can see there is another signature PE that is called signature. It is also a signature PE. It contains 4 bytes, and then next you will have the file header and optional header and other sections as well. So this MZ is the major indicator that it is a PE file, and also the words PE in the signature field are also an indicator of the PE file format. So if you go and open this any process, so let's say any of these exes, so these DLLs are also PE file format. You can select anything and open this, and you can see the starting 45A MZ, and also at the offset 018. So 018 108. So you can see 108, you can see the PE. In the same way, you can open any other DLL. The starting 2 bytes will be 4D5A MZ. So in order to write a loader that parses all of this, first you need to have a tool that parses and shows the information for you. So we are going to use the tool called PE bear, and you can load the PEs, and you can go to, we are going to load the kernel32.dll. So here, if you first visualize the PE file format, then you can write the code accordingly. So go to the DOS header and you can see the 0. This is called magic number, 4D5A. So it is actually 5A 4D in memory. So the PE bear shows you in the hexadecimal format. Each number is a hexadecimal, and the last field contains the pointer to the signature, and the file header, optional header, section headers, exports, imports, base relocations. We are going to touch all of these. So for example, the exports. So this kernel32.dll exports so many functions. You can see all of these functions. That means you can import this kernel32.dll and use these functions. And also the forwarder, you can see some of the functions are not implemented inside this DLL, but it uses other DLL called kernel based.dll. So you can see the format is DLL name dot function name. So if you have a forwarder, then what you need to do is you need to copy the string and load the kernel based.dll, and then again get the address of this function. So we are going to resolve the forwarders as well in the upcoming videos. So that's all about the introduction to the PE file format. In the next video, we are going to see about the image DOS header. Hello everyone, in this video we are going to see the image DOS header of the PE file format. So in the previous video we have seen the introduction. So the first 64 bytes of a PE file contributes to the image DOS header. You can go ahead and open the PE bear and go to the DOS header, and you can see the magic number 5A4D. and also the last member, that is the offset to the signature. So the first thing is we can get the base address of our process loader test.exe, and let's run this. So this is the base address. So what you can do is you can cache this address as a pointer to the image DOS header, because the first bytes will be the 4D 5A. So what you can do is image DOS header, a pointer to DOS header is equals to DOS header pointer and DLL base. Now we can go ahead and print the contents of magic and the offset. So the first one is magic DOS header e underscore magic. So this is the member name. You can see the all the members. The only two members that are we are interested are e underscore magic and the e underscore LFA new. So LFA new is the pointer to the signature, that is the PE. So we have seen this last 4 bytes are the offset to the signature. So DOS header e underscore magic std and also ELFA new DOS header e underscore ELFA new. So if you get the right magic number, then that means you have got the correct base address. And you can see the 5A 4D, it's in the memory, so that's why we got the 5A 4D in the reverse, and the ELFA new is 100. So in memory the Little Indian order, so you need to read the 4 bytes from the right to left, 0000 0100, that is 100. So this is the ELFA new. So what this means is if you do DOS header plus ELFA new, sorry, DOS header plus DOS header ELFA new, so this gives you the pointer to the signature, pointer to the directly the signature, bypassing this rich header. After the file header you will have the after the signature you will have the file header and optional header. But that's all for this DOS header video. So that's all we need to know about the DOS header. So in this video we are going to see the signature, how to get to that point. So this rich header is a dynamic in size, we do not know the size of this, so that's why the DOS header contains the offset to this signature. So we can say char star DOS header plus DOS header e underscore LFA new. So we are jumping from this to this by reading this offset. So from 00 plus 100 gives you this offset. So and it is D word pointer signature D word pointer. So this pointer is pointing to 4 bytes because the signature is 4 bytes. So what I can do is I can print the signature by using the star dereferencing the signature. So remember, all of this occurs inside our own process. That's why we are able to dereference the addresses and get the values. If you want to parse the contents of another process, you need to use the Windows API read process memory and the write process memory to read and modify the memory. So since the DLL is getting loaded into the target process by our DLL injector. So that DLL runs under the context of the same process, and it can happily fetch the addresses and dereference that and get the values. So let's go and run this. So this is our own process, so that's why we are going to happily fetch the addresses and dereference that, read the contents easily. And you can see the 4550. So that this is the hexadecimal. So this is the 4550. You need to read these 4 bytes in the reverse order in the Little Indian format, that is in memory 00004550. So that is how we read this 4550. So that means we have successfully got to the signature point bypassing the rich header. So that's all for this video about the signature. So the only way to get to that is either you need to read all the bytes and search for PE00, otherwise go to the DOS header, read the ELFNU and jump to that offset. So that's all for this video about the signature. So in this video we are going to talk about the file header. So this comes after the signature 4550. So it contains these members: the machine, sections count, size of the optional header, and the characteristics. So the first one is the machine. You have the machine value to which this binary has been built. It can be 32-bit AMD 64 or even the ARM processor here. For now we are dealing with the 64-bit binaries, so it has been made for AMD 64. And the sections count 8. So after the optional header you will have the sections. This sections count is placed inside the file header, and there are 8 sections in the kernel 32.dll. And the size of the optional header, so this is very huge one. This is the optional header. This follows after the file header, and the size of the optional header varies. So that's why the size of this optional header has been placed here. And the characteristics of this file, file is executable. An app can handle 2 GB greater than addresses, and the file is a DLL. So these are the bit flags that are specified to indicate the type of the file. So let's go and print these. So how you are going to get is DOS header. We are at the DOS header. We are going to first get to the signature DOS header ELFNU, and the signature is 4 bytes. So you add +4 to this DOS header offset. This is image file header pointer. File header is equals to now we have reached at the file header. We are going to print. So we can just copy this, print the machine file header machine, number of sections, and then the size of optional header. So we can go and print this. So we have got the machine 8664 and the number of sections 6. Size of optional header is F0. So we are parsing the contents of loader test.exe. So that's why we have got the different values. What you can do is you can change this to kernel 32.dll, and now you should see the same values, and you can see the 8 sections like we have seen in the PE bear. You can see here 8664, 8 sections, and the size of the optional header F0, 240 in integer. So that's all for this about the file header. We have three major important fields: machine, number of sections, and the size of the optional header. So in this video we are going to talk about the optional header. So this is very important header, and also it contains many fields. So the first field is the magic NT64, and the size of the code section, and size of initialized data, uninitialized data, and the entry point. So this is the address of entry point. So if you calculate the base address plus entry point, this is where we need to execute the code, and base of the code and image base. So this is called the preferred image base. Every binary have this same number, and it just prefers to be allocated at this base, but not every process can be allocated at this address. So we need to manage we need to manage some addresses, so the image will be loaded at the different address. So we need to fix those relocations. So those are called base relocations. We are going to fix them in the future videos. So we need to find the difference between the preferred image base and the actually loaded image base, and we need to calculate the difference and add that difference value to the addresses that are needed to be relocated. So some hard-coded addresses will be will be present according to this preferred image base. So we need to modify them so that they will work anywhere when we loaded the image. So that is called fixing the base relocations. We are going to do that in the upcoming videos. And the section alignment, file alignment, and we have the size of image. So this is the size of image in memory, and the size of headers. So this size of headers is the total size of all these headers from the DOS header, signature, rich header, file header, and the optional header, and also the section headers. So what we can do is we can directly paste from the starting DOS header to this size, and all the headers will be placed accordingly. So after this size of headers offset, you will receive you will face the actual values, actual section contents, and the DLL characteristics. And here you have the data directory. So this directory contains the virtual size, so virtual address and the size. It contains the offsets to the export directory, import directory, base relocations, and so on. So if you go to this click on this address, you will go to the exports, and that is what exactly this points to, exports. So that way the virtual address and the sizes are stored in this array of data directories. Export, the first one is export, import, and the fifth one is base relocation. So we are going to be use these values. So let's go and get to the optional header. So you have two optional headers. One is the optional header 32, and another one is image optional header 64. We are going to use the image optional header 64. Optional header is equals to image optional header 64. So starting, we are at the DOS header. So after the DOS header, we are going to get the ELFA new offset, DOS header ELFA new plus the signature is 4 bytes plus, and the file header. The file header follows the signature and size of image file header. So we have reached the optional header. We can go and print the contents. magic optional header magic. So I'm going to copy this and paste here. We are going to print the address of entry point, and we are also going to size of image, and the size of headers. So the size of headers is very important value. It makes our life easier. Without this, you have to copy each and every header. Image base, and you can print the offsets of export directory and import directory as well. So we can go and run this. So the image base. So here you can see the 20B value, address of entry point 2E1A0, and the size of image C9000, and the image base you can see at the offset 18, that one. So these dealers can be loaded at the image base, the important dealers, NT dealer, kernel dealer. So the concept is these dealers are placed at the particular address when the OS starts, and these are get shared into the processes. So this image base will be the same for each and other process that are importing this kernel32.dll. If you want to import a DLL like kernel32.dll and modify the contents of it, then you need to make a copy. So that is called write copy. So for now, we can assume that, not even assume, it's these dealer base addresses are present equally on all the processes. So that's how we are able to write this reflective loading, because these dealer bases are equal among all the processes. So that's all for this video about the optional header. So it follows after the file header and contains very important members like entry point, image base, size of headers, and also the data directory array. So in this video we are going to talk about the section headers. So after the optional header you have the section headers. These section headers contains information about the sections, where they should load, and the sizes of the sections, and also the characteristics determining whether the code is whether the section is executable, readable, writable, etc. So these are all the sections that are present in the kernel32.dll. So we are going to talk about the raw address and virtual address, raw size and virtual sizes. So the raw address is the address from the raw file. So if this kernel32.dll is in the disk, the raw address of the text section is 1000, and if it is loaded into the memory, the text section should start at the virtual address 1000. Here the values are similar. Let me load another PE file. Let's load our loader test.txt. So if you go to the section, you can see the raw address is 400. So that means this section starts at the 400 offset from the in the file on the disk. But when you load this binary into the memory, this section, text section, should start at the virtual address 1000. So that means if you start your loading of this binary at the 100 virtual address, you need to add the 1000 to this and start writing the contents of these sections. So that is the virtual address, and the raw size is the size of the section on the file, and the virtual size is the virtual size of this section when loaded inside the memory. So why these two are different means, sometimes the alignment, there will be null bytes after the section bytes to make this aligned to the file alignment. So that's why the remaining bytes will be filled with null bytes, and the virtual size, it can be virtual file alignment and section alignment 1000. So sometimes you do not need those null bytes in the virtual size. So that's why you will see mostly the virtual size being lesser than the raw size. So here you can see here, so the dot data raw size is 200. So it is very smaller, and the virtual size is 680. So that means so much of data is being mapped when loaded into the memory. So this data can contain variables, etc. So we have declared some strings, those can go into this dot data section, increasing the virtual size than the raw size. So this is the concept of this raw address and virtual address. So if you read the contents at this raw address, sometimes you need to convert that relative virtual address to the file offset. So suppose this binary has been loaded inside the memory, and you have read some address that is 1200. So when the 1200 address is at the 200 offset from the virtual address, but you want to locate that exact address at the raw file when on the disk. So that means if you go and take the 1200 and read the raw bytes from the file, you will get the wrong values, because this is the virtual address and the 1200 is only meaning to this virtual address. So you need to find the difference between the 1200 and the virtual address 1000, that is 200 hexadecimal, and you need to add the 200 hexadecimal to this raw address to get to that point inside the file on the disk. For our kernel 32.dll, these are equal, and you can see the raw address and virtual address for relog section is, and also the resource section, and these sections are different. So let's go and parse these contents from the C++ code. So this section header start after the optional header. So that means first you need to fetch the section header pointer to this text section. So image section header pointer section header is equals to, so what you can do is I can simply copy this code here and paste here, and we need to add the size of the optional header. So how you are going to get is file header size of optional header. Remember, you should not use the size of this structure, you should use the file header size of optional header. Now we have reached at this point pointer to the starting of the first section. So you need to loop through the section headers and print the contents. So how you are going to do this is, we already have the number of sections inside the file header. So for int I is equals to 0, I less than file header number of sections I plus plus, and for every iteration what you are going to do is, you are going to increment the section header, and we can go and print the section names. And one more thing is, the section names should not be greater than 8 bytes. So that is the limitation. So section name, section header name, std I can go and copy section raw address. So this is the pointer to raw data, section virtual address, and we can print the raw size. And also print the virtual size. It is in the misc.physical address and the virtual size. We can print the characteristics as well. So in the upcoming videos, at the ending of our writing of our reflective loader, we are going to check these characteristics and assign the memory accordingly. So we are going to assign the page protections accordingly. So for now, let's go and print this. And you can see we have printed all these sections. So it's let's print a new line here. So you can check the values here. We have got all the sections, dot text, raw size, virtual address, and virtual size. So we have got all the contents of this section headers. So these are also very important. These determine how the section should be loaded inside the memory. So that's all about these section headers. These follow after the optional header, and the number of sections are indicated by the file header, number of sections, member. Hello everyone, in this video we are going to see the exports. So the DLL file have the exports, the exe file will not have the exports. You can see here there is no exports section. If you go to the optional header, and the export virtual address is 0 and the size is 0. So only the DLLs can export some functions, so that the other applications can import those functions and use them. So to get to this exports, what you need to do is you go to the optional header, you have the data directory. The first member is the export directory. It contains virtual address and the virtual size. So if you click on this and you go to the exports, so that is the same offset A4D30, and you have some members in here, the characteristics, major version, minor version, and the name. So the name contains the name offset. So RVA stands for relative virtual address. So wherever your binary has been loaded, you need to add this number to get to this kernel32.dll. So if I go and click on this, you can see the bytes kernel32.dll and the null byte at the end. So this is called relative virtual offset. So wherever the binary has been loaded, you need to add this number to that loaded base address to get to this kernel32.dll. So okay, after printing this, you have the number of functions, number of names, address of functions, address of names, address of name ordinals. So we are going to take a look at all of this. So let's go and first get to this exports first. So how you are going to get through the exports is optional DLL base plus optional header dot data directory of 0 is the export, the first one, dot virtual address. So this is the image export directory pointer, export directory. So we have reached at that point. So the dealer base, this is the actual base that has been loaded, and the virtual address is the relative virtual offset. So if you add these two, you will be received, you will be placed at the starting of this export directory. Now I can go and print the dealer name. You can also add another check if optional header data directory of 0 dot size. So that means we are checking if the size is 0 or greater than 0. If it is 0, then we are not going to inside this export directory, because there are no exports. So you can cut this and paste here. So we have the uh, dealer base plus export directory name, the name of the dealer. If you add these two, you will get to the bytes where the kernel 32 dealer has been. So we can name this as char star dealer name. Now I can just go and print the contents dealer name, dealer name. So let's go and run this, and you should see the kernel 32.dll in the uppercase. Now we are going to see how to parse the exported functions. So here the number of functions is where there is a number of functions and number of names. So we are going to parse through the number of names. So address of functions. So if you, this is an offset to the 8-byte pointers, 8-byte values. You have these addresses and the number of address of names. If you go to this offset, you will have the 4 bytes of another relative offsets. So you can read the first 4 offsets. So that is A8F87. So this is the A8F87. This is the name RVA. So if you go to this offset and add +2, sorry, the +2 is for imports, my bad. So if you read the first 4 bytes and add the RVA to the loaded base address, you will get the function name. And in the similar way, you can read the next 4 bytes, that is A8FC0. So the PE bear has already read these values and it is showing in this column. So you can see A8FC0. So this is the value. If I go and click on this, you will see the function name. And in the similar way, the name RVA of the third one and the fourth one, etc. So all you need to do is go to the address of names pointer and start reading 4 bytes, 4 bytes, 4 bytes until you will receive this, until you complete the number of names loop. Some functions are also exported through ordinal, but we are going to see only for the names, because most of the functions are exported through the names. So what we are going to do is, for int I is equals to 0, I less than export directory number of names I plus plus. So before that, what we are going to do is, we are going to store all of these pointers in 3 variables. And the third one is, I forgot to tell you, address of name ordinals. So how you are going to retrieve a function address for this function acquire SRW lock exclusive is, you read the corresponding index of this name ordinals. So this acquire SRW lock exclusive is the first member, right? So this is the first member, and you read the first member of the 2 bytes inside this address of name ordinals offset. So go ahead and read the first 2 bytes, that is 0. So that is the index into the address of functions. So you take this value 0 and go to this address of functions and read the 8 bytes, 4 bytes from this index. So the 0 into 4. So that is, that is the first 4 bytes. So the index 0, So that is A8F 9F. So that is a A8F 9F. So this is a forwarder. So we are going to see that later. Uh, so the forwarder lies inside this export directory. You need to identify whether it is a forwarder or not. You can see here it lies along these offsets A. So let's take another example. So that is the third one. So the third one is A8F F3. So that is the activate act CTX, and the function RVA. So this is the index 2. So inside this is the index, third index, 1 2 3, and you go and read the 1 2 3. So that is the index 2, and go to the index 2. So that is 0 1 2. So 3 7A F0. So 3 7A F0, that is the function address. So let's first store these values inside three variables by adding the loaded DLL base. So these are all the relative virtual addresses. So what I'm going to do is, so u long long, so I'm going to declare address of functions as a EAT pointer, export address table, DLL base plus export directory address of functions. And copy this. And second one is ENT pointer, export name table, address of names. And the next one is EOT, export ordinal table, address of name ordinals. So what I have done is I have took these three relative virtual addresses and added to the dealer base and stored them in the corresponding variables. So let's go and first print all the function names that this DLL is exporting. So the ENT pointer lands at this point. So what you need to do is you need to read the 4 bytes from this. So we can say name RVA is equals to ENT pointer plus index into 4 bytes, I into 4. So we are already looping through this number of names. For each loop, we are going to increment 4 bytes in the multiples of 4 bytes. So in the first loop, we are going to read the 4 bytes and the next 4 bytes and the next 4 bytes and so on. So the first one is this one A8F87. So that is the name RVA. So what I can do is I can do the dereference and get the name RVA directly. Now I am going to add the DLL base plus name RVA. So if you go ahead and add this name RVA to the DLL base, you will get to the bytes of this function name. Char star function name. Now I can go and print the function name. So we can go and run this, and we can see we have printed all the functions that the kernel32.dll exports. So there are a lot of functions, and you can see the starting functions as well. and now we are going to read the 2 bytes from the name ordinals array. We are going to read the 2 bytes. So char star EOT pointer press I into 2. So word ordinal is equals to word star. So what this does is we are reading as a word pointer and dereferencing to get this index value, the ordinal value. Now what I'm going to do is with this ordinal as an index into this address of functions, EAT pointer. So char star EAT pointer plus ordinal into 4. Not the index, not the index I, but the ordinal into 4. So ordinal is 0. So we are going to read the 0 into 4, 0. So that is the starting 4 bytes. D word func RVA, function RVA is equals to D word pointer. So we have read the function RVA, and what we are going to do is we are going to add that to the DLL base. So u long function address is equals to DLL base plus func RVA. Function address, function address. So that's how you can find the function address. Okay, there are so many functions, and we can see the function addresses. And if you go to the bottom, so one way to verify very easily is you can read the last bytes. So 58370, that is the offset. So that means probably the kernel 32.dll has been loaded at 800000. So that's why you have this function RVA 58340, etc. So you can see 58320 here. So this is how we can read the function address. So we can actually write the function force inline u long get DLL export function address and constant char star function name to find. So what I'm going to do is okay, also it also takes the DLL base address, my bad, u long DLL base, because you need to supply the DLL base, and from there onwards this function parses and finds the function address. So let's go and copy all of this. Copy all of this and paste here. So let's check from the beginning. We are at the DOS header. We are going to comment out the print statements, because this is an inline function. We should not depend on third party, and we are reading the signature. And the file header, optional header, and we don't need the section headers. So we are going to delete this. So here we have the pointer to the DLL name. Now we are going to check if my strcmp of DLL name and the function name to find. So that means we have so if this is our function, then Sorry, my bad, not here, it's here. Function name. So if the function name is matches our function name to find, then we are going to return the function address. Otherwise, by default, we are going to return 0. So okay, let's test this. Get DLL export function address of DLL base comma constant char star func1 is equals to message not read process memory func1. We can say auto as well to automatically differ the type. Func1 address. So let's run this. So read process memory at 3B780 and 3B780. So we have successfully retrieved the function address. So that's all for this video. In this video, we have seen how to parse the exports and the functions. So we have also written the inline function that calculates the function address and returns. Otherwise, it is going to return 0. So in this video, we are going to see how to resolve the export forwarders. So for example, you can see the function name here, acquire SRW lock exclusive. It has a forwarder. So the functionality was not implemented in the kernel 32.dll, but it was implemented in the NTDLL. So you have to fetch the NTDLL base address and then fetch the address of this function RTL acquire SRW lock exclusive, and then you need to do whatever with that. So here let's take the same example. Double click on this function name to copy the text and paste here. Now let's go and run this one. You will see the address, you can see the last bytes matching with the 8F9F. So 8F9F, A8F9F is a offset to the string ntdll.rtl acquire srw lock exclusive. It is not a function valid function address, it is just a pointer to the string, the forwarder string. So one thing you can prove is you can directly print the address as a character pointer. So the std cout will print the contents of the func1 address. So let's run this, and you can see the forwarder string. So this is not a valid function address. If you try to execute as a function pointer, then you will get an error. So your reflective DLL code gets failed. So that is why we are going to resolve this forwarder. So how is we are going to read two paths. First part is the DLL name and the second part is the function name. These two are separated by dot. So you are going to maintain two arrays, for the one for the function name and another for the so one for the DLL name and another for the function name. So let's go and do that. So inside our get DLL export function address, if we have found our function address, we have to check if the function RVA A8F9F F9F is in between the export directory. So uh, what that does mean is that because this function RVA is not a function that is somewhere in the code, but it is actually a pointer to the string that is inside the export directory. So in this A4D30 plus EC78 and A4D30, so that means this uh, pointer lies in between this memory address, so this RVA. So that means if our function RVA lies in between the export directory and the end of the export directory, then that means this is a export forwarder. So if you take a look at the third one, it does not have a forwarder, but it does not lie in between this A4D30 and A4D30 plus the export directory size. You can see here it is starting with 37i0. Only the forwarders, if you take a look at the forwarder, it is starting with A. So this is indeed belongs to the forwarder inside the export directory. So you can check for any of these values. So let's go and do that. So we already have the func RVA. So we are going to check if func RVA greater than or equal to export directory, optional header data directory of 0.virtual address, and also the func RVA should be less than the optional header data directory 0.virtual address plus optional header data directory of 0.size. So this indicates that our function RVA is in between our export directory virtual address and the size. So our function is export forwarder. We can store the example here for our convenience. So we are going to write another function. So let's call this as force inline resolve export forwarder. It is going to take the forwarder name pointer. So it takes the pointer to this string and it is going to divide this string into two parts, one for the DLL and another for the function name. So return resolve export forwarder of and pass in the this address, that is the DLL base plus the function RVA. So pass in the function address. So you can see here we have a function that calls this function. So what you can do is you can just declare this. So it has some nested dependencies. We are going to declare these two functions. So if you declare these two functions, you can use them nestedly. So in our resolve export forwarder, we are going to use the same function get DLL export function address. So that's why it has the nested dependencies. So now we have got the a pointer to the forwarder name. So this is this one. So now we have this forwarder name pointer. By default, let's return 0. So let's create a two arrays. So make sure you allocate array of size 128. Do not allocate array of size 256. Uh, your loader gets error and it will not execute properly. So make sure you have less number of bytes. And also make a pointer for this. DLL name to find PTR is equals to DLL name to find, and also function name to find PTR is equals to function name to find. So okay, we have two arrays, two pointers pointing to the starting of the arrays. Now we can make copy forwarder name PTR is equals to forwarder name. So what we are going to do is we are going to traverse through the string bytes and stop until the dot. So if you face dot, then that means this is the end of the DLL name. So while forwarder name pointer not is equals to dot star, dereference this. So while star forwarder name pointer not is equals to dot, we are going to say star DLL name to find PTR is equals to star forwarder name pointer. So we are dereferencing the first byte, first character n, and storing it in the DLL name to find. And afterwards we are going to increment this both pointers. Whenever our forwarder name pointer reaches this dot, we are going to break the loop, and after breaking the loop we are going to advance one byte after this dot, so that we will reach at this function name. So now forwarder name pointer points to this function name at the starting of this function name. And also the DLL name contains ntdll, so you need to have a DLL like ntdll dot DLL. So we need to append these 4 bytes. So what you can do is star DLL name to find pointer is equals to dot and increment the pointer, and copy this, paste here, and change this to dot DLL. Okay, so we have appended the ntdll, we have appended the dot DLL, and the next byte will be automatically 0 because we have nullified the array by default at the declaration. So now we are going to parse traverse from this function name to the end and store all these bytes inside this function name to find again. So we can just copy this while loop and paste here, and change this to function name pointer and function name pointer. And also add forward name pointer not is equals to 0. we need to add, make this to end. So the forward name pointer must not be okay, so we can just remove this, my bad. So the forward name pointer now points from the function name. There is no dot, there is only null byte at the end. So we can say while forwarder name pointer not is equals to 0, then we can copy the byte. Now we have the dealer name inside this array and function name inside this array. So what we can do is we can use our function get DLL base address, and pass in the DLL name to find, and you will return the forwarder DLL base. If forward DLL base not is equals to 0, then that means you can use this function again, get DLL export function address, and pass in the forwarder DLL base and the function name to find. Now you will return, you can just return this value. So in this way you can use the nested functions. So this function uses get DLL export function address, and get DLL export function address inside uses the resolve export forwarder if it faces a resolver. So that means you will recursively deal with all the exports. Now let's go and print this. So previously what we have received is A8F 9F at the end. Now if you go and run this, and you can see the actual address. So you can see this is different from what we have received previously. Previously we have received the A8F F9F, but here you got the totally different address. So let's verify that. So you can load the ntdll.dll and go to the exports and search for so RTL, my bad. So the exported value is RTL acquire SRW lock exclusive. So go to that RTL acquire SRW, sorry, this one, and you can see the offset here, function RVA 6B6 6C0. So 6 sorry, my bad, RTL acquire lock exclusive. So this one 6B6 C0. So maybe it has NTDL has been loaded at 66000. So that's why if you add that, you can see the 6 has been gone into 2, and the last 4 bytes B6 C0 has been correct value. So we can check that get DLL base address of ntdll.dll auto ntdll base. So let's print the ntdll at ntdll base. So let's run this. Now ntdll is at 725C1000. So you can go and open the calculator. So what I'm going to do is 5C 4 zeros. So this is the address at the NTDLL, and I'm going to add the function RVA plus 6B 6C0. Sorry, my bad. I just and you can get the value 6 to B6C0. So you got the exact value. So you can see the last bytes are equal to this calculated value. So that means we have successfully retrieved the forwarder address. We have resolved the export forwarder and retrieved the uh, destination address correctly. So that's all about the resolving the export forwarders. So we have seen how to resolve the export forwarder. We have to check if the function RVA lies inside our export directory, then it is a export forwarder. Then we have resolved the forwarder by dividing it into the DLL name and the function name, and finding the DLL base and the function address, and returning the value. So that's all for this video on the resolving export to forwarders. Hello everyone, in the last video we have seen how to resolve the export forwarders. In this video we are going to parse the imports. So imports are very important because every exe file imports DLLs and uses the functions. So even the DLL also imports the functions. So how to get through the imports is, we go to the optional header and look at the second index, that is the import directory. It has the virtual address and the size. So this is the RVA. So you can click on this and you can see the first you can see some of the bytes have been highlighted. This is called image import descriptor. So this structure is called image import descriptor. It contains the name, offset, and the function count, and it does not have the function count. So original first thunk. So original first thunk contains the name pointers, and the first thunk contains the addresses. So in the original first thunk you can see the offset here. If you click on this and you go to the array of the name offsets, so if you read the 8 bytes, you can see here the B6DEE. So that is the B6DEE, that is the original first thunk name RVA for this RTL compare memory. So you read the 8 bytes and go to that virtual address, and you can see the from index index 3, you can see the function name here. So you need to add +2 to get to the name. So that's how you going to parse. After reading the first 8 bytes, you can read the next 8 bytes B6DDA. Go to that and add +2, and you can see the name of the function. So we are going to loop through the original first thunk and the first thunk. So original first thunk contains the pointers to the name of the functions, and the first thunk should contain the addresses of the functions in the runtime. So at the on disk they both contain the same information, original first thunk and the first thunk, but when the image has been loaded inside the memory, the first thunk pointers should point to the actual function addresses. So that means if you are loading a image manually, then you are going to find the function address of the RTL compare memory and then write that address at this first thunk. So for the first thunk, it is for the RTL compare memory, it is the first index. So you write at the first 8 bytes. So that's how we are going to parse the imports. So for each DLL, we are going to call the load library, and we are going to load this DLL, and then use the get proc address to get the function address and write at this first thunk. So that's what we are going to do. So inside our loader test C++ program, we have already parsed the exports. So we have the optional header data directory of 1. 1 is the index to the import image import descriptor, the virtual address, image import descriptor, import descriptor, add the DLL base, and we can also check the if the imports size is 0 or not. If a binary does not have imports, you will see the size 0. So optional header data directory of 1 dot size, then only we are going to move forward with the parsing imports. So the image import descriptor has the name. First we can loop through all the DLLs. So while import descriptor name, so if it has a name, then we are going to print that name. Name is also the RVA, relative virtual address. So B6E02, if you go to B6E02, you can see the DLL name. So that is DLL base plus import descriptor name. So char star DLL name, we can go and print the DLL name. Import DLL name, and afterwards we can increment the image import descriptor pointer, import descriptor plus plus. So this will automatically increment the size of the image import descriptor. So we will face the null structure at the end of all the DLLs. So we can go and run this, and you can see we have printed all the DLLs. So these are the exact same DLLs. Imports for the kernel 32 DLL. Okay, so far so good. After printing the DLL name, we are going to parse all the functions that are being used from every DLL. So that is the original first thunk. So we are going to retrieve the pointers for the original first thunk and the first thunk. So original first thunk is a RVA. So that means wherever the DLL has been loaded, you need to add this number to get to that point. So DLL base plus import descriptor original first thunk. So let's call this as u long long pointer og first thunk. Why u long long pointer means because we have to read the 8 bytes. So if you cached this address as a u long long pointer, you can just dereference the variable and read the 8 bytes. So okay, u long long pointer. Make sure the same for the first thunk pointer. So name this as pointer, change this to first thunk. So we are at this point, and now we are going to read the 8 bytes. So while star og first thunk pointer, so this indicates that we are checking if it is a not a null, not a zero value. If it is a zero value, obviously we are going to not go into this loop, we are going to walk through the next import descriptor. So while this value is not is equals to null, so u long long func name rva is equals to star og first thunk pointer. We are going to dereference this value and get the rva, that is b6dee, b6dee, and you need to add +2. So we have the function name rva. We can go and print the function name func name rva, and afterwards we can increment these two pointers, og first thunk pointer plus plus and the first thunk pointer plus plus. So why do we need first thunk pointer means we have to write the address of this function name, address of the function in this first thunk array. That is how load library works. So we can go and run this. Oh sorry, my bad. We need to add the DLL base plus og first thunk pointer plus 2. I'm sorry, my bad. Char star function name is equals to, so we have retrieved the function name rva, that is rva. We need to add the DLL base. So let's run this. And we can see we have printed all the function names. So you can see the get console functions and other functions from the DLLs. So we have printed all the function names. We can also print the first thunk values, first thunk, and the first thunk is the DLL base plus the first thunk rva. So we are at this point, and we can just print the first thunk pointer value, because this pointer is necessary. So this address is necessary when you want to write the function address to this first thunk pointer. You no need to star, because uh, that is actually fetching the value at that address. We do not want to fetch the value. We just want this address, so that we can write the function address. And we have printed all the first thunk values. So what we can do is we can write a function that will take in the function name pointer and gets the first thunk pointer address, so that we can write the function address at this first thunk pointer. Force inline get import first thunk constant char star u long DLL base and the function name. So we can copy up to DOS header, up to the optional header. So after retrieving the optional header, we can just copy this code of the imports what we have just written and paste here. So let's see this. We are getting the DOS header, signature, file header, optional header. If the import size is greater than 0, otherwise we are going to return 0. So we can comment out this import DLL name. So comment out these names and use our mystrcmp function name and the okay, let's modify the function argument name to function name to find and pass in here. These two are of character types. If we have found the function name, we have to return first thunk pointer. Cast this as u long and that's it. Our get import first thunk address function has been implemented successfully. We can test this out. Get import first thunk of DLL base, comma, let's run this, and we got the address value 88AB10. So we have retrieved the first thunk address successfully. So this function will be helpful if you want to do the DLL hooking. You can directly get the first thunk address of the function and directly modify this value to your malicious function. So this is the IAT hooking. This technique is called IAT hooking, where you modify the IAT table and write your malicious function address at the first thunk, and inside your malicious function you will modify the parameters, or you want to do something else, you can do that. and return the actual value, the function return value, so that it will be like a normal behavior. So that's all for this video. In this video we have seen how to parse the functions from the imports, and also how to retrieve the first chunk uh, pointer values. So in this video we are going to look at the base relocations. In the previous video we have seen how to parse the imports. So what are these base relocations and why do we need to fix those? So in the optional header, if you go to the fifth index 0, 1, 2, 3, 4, 5, you can see a RVA to the base relocation, and if you go to that you will land at this base relocation. So it contains two members, page RVA and the block size. So the page RVA is the RVA to the page from the base address, and the block size indicates the number of entries in this the total block size. So first let's see what are these base relocations. So if you go to the page RVA, and you can see some addresses here. The first relocation RVA is 87008. So that means you need to read 8 bytes from this, and so if you read those 8 bytes, you can see the address 18008 E200. From the Lithuanian byte order, you need to calculate from the right to left 018008 E200. So if you can see, this is a hard coded address. In the optional header, the image base is 18 zeros. So this address has been hard coded according to this one. So if you go and load the kernel32.dll in some other base address, so this address becomes invalid. So what you need to do is you need to find the difference between the assumed base address and the loaded base address, and that value is called delta, the difference, and you need to add this delta to this value. So you need to read the 8 bytes, add the delta, and write the new value into these 8 bytes. So that is what the base relocation is. These are all hard coded addresses. You need to they have been written here based upon the assumed image base. So you need to find the difference between the assumed image base and the loaded image base, and add the difference to these addresses. And the block size, you can see the block size is 1 BC. So the first 8 bytes, so the first 8 bytes contributes to the base relocation information. So the first 4 bytes is the page RVA, in which page the relocation entries are present, and the next one is the block size 1 BC, and followed by the 4 byte values. So these are the offsets. So A008, A018, A028, etc. So the A stands for the 64 bit. So this is a 64-bit binary. The A indicates that it's a 64-bit field, and you need to calculate the 8 bytes. So okay, first let's get to this base relocation. So if optional header data directory of 5 dot size zero is export 1 2 3 4 5, base relocation is equals to DLL base plus optional header data directory of 5 dot virtual address. So we are at this point and we have two members: base relocation, size of block, and virtual address. So while base relocation, virtual address, so we are going to loop until this virtual address is not is equals to null. And how to loop, how to get to the next base relocation block is you need to add the size of this first block. So we are at this position C7000, and if you add 1 BC you will get to the next base relocation, that is this one. So you can see this these 4 bytes 08 80 100 is the next page RVA of the next block. So if I go and click on this, you will land at this point. So I'm going to click on this and you can see we have landed at that point. So that means from our current base relocation address you need to add the block size to get to the next base relocation block. And if you are at the end of these blocks, you will notice null values. So sorry, my bad, there are no null values. What you need to do is you need to make sure you have fulfilled this size. So the size of the base relocation table is 5d8. So what you need to do is you need to loop through until you have satisfied this size 5d8. So let's say auto total size is equals to optional header data directory of 5 dot size. This is the total size, while total size we are going to loop until this total size has become 0. So total size minus is equals to total size minus base relocation size of block. So we are decrementing the size of block from this total size. So that means we have parsed this base relocation block. We have to loop through this base relocation as well. Base relocation location is equals to so how do you get to the next base relocation block is at this current point you need to add this block size base relocation plus base relocation size of block, and make this as char pointer. So we are at this point and we are going to add the size of block to get to the next base relocation, and in the next iteration we are reducing the total size minus base relocation size of block. So okay, so we are at this block, we are going to print the page RVA page RVA virtual address and we are going to print the block size as well. So let's go and run this one, and you should see the values here: 87,001 BC, 88,001 BC, 89,038, etc. and so on. C6002C. So we have successfully parsed the base locations. Now one more thing is we have to read these entries. So we need these values, the relocation RVS So from the in the base relocation block, the first 8 bytes have been occupied by the page RVA and the block size. So how you are going to count the entries is, so let's go auto entries count is equals to base relocation size of block. So the size of block indicates the total size of the block, which includes the first 8 bytes that are related to page RVA and the block size. So we need to subtract 8, and then you will have the size of all the entries, and each entry is of 2 bytes. So you need to divide this number by 2. So that gives you the entries count. So we have to loop through these entries and read the corresponding base relocation values. So for int I is equals to 0, I less than entries count I plus plus. So d word pointer base relocation RVA is equals to. So we should start at the 8th onwards, because the first 8 bytes have been occupied by page RVA and the block size. So from the 9th byte onwards, we need to read in the multiples of I. So char star base relocation plus I into plus 8. This gives you from the starting of the first entry plus I into 2. So cast this as d word pointer, sorry, word pointer. D word means 4 bytes, so word is 2 bytes. So we have read this A008. We can even do dereference here, no problem. So we have read these entries, so we can go and print this base relocation RVA. So let's run the program, and you can see all of these entries. You can confirm them. Go to the last one and you can see the A00, A008, 10, 18, 20, etc. So the A indicates, let's write here A008. So the A indicates it is a 64 bit value. So we should ignore that one and take the remaining value and add that to the page RVA. So how you are going to do is, if base reloc RVA, do the end operation with the hexadecimal 0FFF, and if this value is equals to 0x sorry, my bad. First we need to, okay, my bad. So we need to end this with F000. So that gives you the only first so the first hexadecimal character A, and the remaining 3 characters will be 0. So if you do the F000, you will be left with the whatever the value it is in the first character. So if it is A000, then that means we need to read this value and cut off this A. So we are going to cut off this A. We can just base reloc RVA and 0x 0FFF. So this first 0 will cut off this A with the end operation, and the remaining value will be auto new RVA. So this new RVA must be added to the page RVA. So we can say base relocation virtual address plus this value. So this new RVA has been calculated. This you can see the value is 87008. This must be our value. We can go and print those reloc RVA. So we can go and comment out this one. So now we can go and see the first reloc RVA for the first block. So the first one is 87008 and 87018, 2858, etc. and so on. So we have successfully found these reloc RVA, and what is left remaining is you need to go to this reloc RVA, DLL base plus reloc RVA, and read the 8 bytes and find the delta between the difference between the loaded image base address and the assumed image base address, and add the difference to this value and write again to this address. So that is what we are going to do in the upcoming video, where in the writing the reflective loader. For now we have completed parsing the base relocations. So that's all for this video about the parsing image base relocations. So in this video we are going to write our reflective loader DLL code. Up to now we have seen how to parse the PE file format, exports, imports and base relocations. Now let's go to our DLL project that we have created at the starting of this course. So what we are going to do is we are going to copy all of this helpers.h code and paste it here. So the idea of this reflective loader DLL is we are going to export a function test, or you can call this as loader, whatever you want. So this we need to write another injector program that can download the DLL from the file or download from the internet and inject into the remote process and calculate this test function and execute this test function. So that is the concept. So what this test function does is it has so this test function will allocate a new memory area and copies all of these DLL contents and also copies the contents, copies the sections, resolves the imports and fixes the base relocations, and at the end of the code we are going to execute the entry point. So this is actually like parsing the PE file. Instead of parsing, we are going to load this raw file into the memory and execute the code of the at the entry point. So first we have to fetch suppose let's use something. Let's use a message box here to pop up a message box. If let's call this as reason, if reason is equals to DLL process attach, so we are going to pop up the message box here. Hello there, and 0. So let's go and compile this one. So open our reflective DLL inside the PE bear. So now there are two exports, DLL main and the test. So we have to write an injector program that loads this raw file reflective order.dll, whether this file can be from the disk or from the internet, and this injector will blindly copy all of the contents and calculates this export address and execute the test function. So inside our test function, what we have to do is we have to fetch the load library and get proc address function pointers, so that we can load whatever our DLL is using. So for now our DLL is using user32.dll, that is as a main primary functionality to pop up the message box. So this is the message box we are popping up. So this is an import, this is a necessary, and this is a dependency. We need to resolve this. So that is why we need to find the function pointers of the load library and get proc address. So we have already seen how to fetch the DLL base address and the DLL export function address. So that is why we have written the helper functions. So I have created a character array. So copy this and paste here. So these are just names. These gets allocated on the stack instead of .data section. So first we need to find the base address of kernel32.dll. So get DLL base address of DLL1. Let's call this as DLL base. So if not DLL base, we are going to return. So if if we have received the 0 as a DLL base address, then we are going to simply return. We are not going to move forward. If we found the kernel32.dll base address, we need to find the function addresses for the load library A, virtual alloc, get proc address, virtual protect, and exit thread. We don't need exit thread, so we just want these function addresses. So we can just say u long load library address, get DLL export function address, pass in the DLL base and the func1, that is the load library A address. So we can just copy this, and we need virtual alloc address, func2, get proc address and virtual protect address. We can add another check if not load library address or not virtual alloc address. So we are checking if any of these addresses are 0, then we are returning. So at this point we have received all these addresses, and one more thing is we need to find our own DLL base address. So this reflective order.dll gets allocated somewhere random in the random memory inside the remote process. So we are executing at this test function. So what we have to do is we need to backtrack. So the function RVA is at the 1030. So you need to read byte by byte and decrement from the memory and reach up to the starting of this DLL file, that is mz. So from from the address of DLL main or the test, we are going to backtrack each byte by byte and check if those bytes are 4D5A. If they are, then we are going to consider this as a DLL main address. So why do we need this DLL main address? Means we need to allocate new memory and load all of this DLL inside that new memory as a fresh copy. where everything will be fixed by us. So okay, so what we can do is we can change this as to kernel 32 base. So auto main addr is equals to ampersand DLL main. So we are fetching the DLL main address. We can also use something return address intrinsic function. We are going to see that in the next video. So if char star, so while star main addr, so we can say while true, if star main addr is equals to m and star main addr plus 1 is equals to z. So what this means is we are at this address, suppose say at this address we are going to read this byte and the next byte. If it is m and z, then that means we have reached the base address of our DLL. Otherwise we are going to decrement this main addr minus minus so we can say auto DLL base is equals to u long long main addr. So this is our DLL base address. We need to allocate new memory and copy all of these sections, uh, all of the headers and the sections, and fix the imports and the base locations, and finally execute the code at the entry point. So let's go and do that. So first we are going to copy this some of this code. So first we need to allocate the DLL. So we need to know the size of this DLL. How we are going to know the size is, we have the optional header and we have the size of image. So this is the size of image in the memory. So for that we are going to copy this code. Image DOS header, file header and optional header. So paste here. And optional header contains the size of image. So we already have the virtual alloc address. So what we are going to do is, we are going to treat this as a function pointer and execute this address. So how we are going to do this as a function pointer means, we are going to define the signature of this function and call that address. So the syntax is the return type LP void and put a star in the brackets to indicate this as a function pointer, and put another brackets to indicate the arguments. So the first argument is LP void and the size underscore t and the d word and d word. And now this is of the type function pointer that takes these parameters and return LP void. Now virtual alloc address. Now this whole address is being treated as a function pointer. You can execute this function pointer using the brackets. So treat entire contents as a function and execute the function. So using the parameters. So the first one is null. The OS will decide the base address for us, and the size is optional header. size of image, and the page protection, allocation type mem reserve and mem commit, and the last one is page uh, execute read write, page execute read write. Don't worry, we are going to change the page protections later for the sections. Now allocate as a page execute read write. So the return value is auto new DLL base. So we have allocated a new memory region for our DLL. Now we are going to copy the contents. You do not need to copy the DOS header, rich header, file header, optional header. We have a member called size of headers. So this indicates the starting. So from 45A, we can directly copy the 400 bytes, hexadecimal bytes, and everything will be copied. All these headers will be copied. So copying headers. So we should not use write process memory. We should do pointer arithmetic for int I is equals to 0, I less than optional header, size of headers I plus plus. So we have our contents at the DLL base. So char star DLL base plus I is equals to char star new DLL base plus I. So we are going to copy byte by byte. So put star here. Sorry, this one is new DLL base, and this one is DLL base. This is the old one. So we are looping from starting byte onwards up to the size of headers and copying byte by byte. So new DLL base plus I, dereference that, and this equal means we are copying from the old DLL base. So we have copied the headers successfully. Now what we are going to do is we are going to allocate the sections according to their virtual addresses. So right now the injector program will not relocate anything, will not do proper allocation of these sections. So we need to copy from the raw address and allocate it at virtual address. So we can do that. Copy the sections code, get the section header. So copy the section, make, okay. So now what we are going to do is, so we are at this section, we are going to copy the virtual size. We are going to copy the raw size. So for int j is equals to 0, j less than section header, size of raw data j plus plus. So the new DLL base plus virtual address plus section header virtual address plus j. is equals to char star old DLL base plus raw address plus section header pointer to raw data plus j. So that's it. From our old DLL base, that is at the raw address, we are going to copy byte by byte until the raw size at the virtual address. So we are going to add new DLL base plus section header virtual address and plus j. So this is the index. We are copying byte by byte the raw size number of bytes. So we have copied the sections. So till now our copying has been completed. Now we are going to fix the imports. So we can see the user32.dll is being imported by our DLL for the message box here. So we need to parse through the imports and load the address at the first chunk. So that is what we need to do. So we can go to our loader test and copy this code, the import code. So copy and paste here. So we need to modify something that, so we are reading the DLL base. The DLL base, the old DLL base which was injected by injector was in the raw format. So we need to be very careful with the RVS. So what we can do is, since we have copied all of the contents, we can do like this. Copy this code and paste here. Now change this to new DLL base. So now our DOS header is pointing to the new memory region where our DLL has been allocated. So we are parsing that as new DOS header, and then from here onwards we have the file header and the optional header. So what we are doing is we are rearranging these pointers from the old location to the new location. So here we have the new location virtual dialog, so new DLL base. So now these pointers are pointing to the new DLL base. From here onwards you don't need to worry about the relative virtual addresses, those will be the same. Okay, so change this to new DLL base. So we have got the function name here, the function name, let's say message box A, and we also have the DLL name. So what we are going to do is we are going to use the load library function to load this DLL. If the DLL is already been loaded, we will just get the base address, we will get the module handle. So load library A, and this takes the file name and this is the DLL name, and user32 DLL will already be on the machine, on the computer. So h module is the return type, and put a function pointer, and it takes lpcstr and load library address, pass in the DLL name, and get the DLL handle. So for every DLL name, for every imported DLL name, we are using the load library to load the DLL and get the DLL handle. And for every function name of the particular DLL, of every DLL, we are going to get proc address. We are going to use the get proc address. So this function takes the DLL handle and the function name and retrieves the function address. So the syntax is for proc the return type and the function pointer, and take in the parameters h module, the DLL handle, and the lpcstr get proc address. So this we are treating the address as a get proc address and pass in the DLL handle and the function name, and we will get function address. Now we have got the function address. What we are going to do is we are going to write this function address at the first thunk pointer. So that is what we have discussed previously. In the first thunk stores the function addresses. It is an array of function addresses. We have to write our function addresses there. So first thunk pointer points to this address already. So star first thunk ptr is equals to function address. Cast this as u long long, and we are good to go. So we are updating the first thunk array with the function addresses. So that is the fixing imports. Now we are going to fix the base relocations. So this is very easy. So go to your loader test project and copy this one and paste before the imports. So we need to paste before the imports. So change this to new DLL base. So at this new RVA, we have got the new RVA. So the new RVA values are 20F8, 2100, etc. So first let's calculate the delta. Auto delta is equals to new DLL base minus the optional header dot image base. So this gives you the delta. So this is the delta we are talking about, the difference between the loaded image base and the preferred image base. So we need to add this value to each and every base relocation. So we have already got the base reloc RVA 20F8. So char star DLL base plus new RVA. So this we can parse this as u long long pointer. So we can call this as address to write. So what we have to do is first we have got the address new DLL base plus the new RVA 20F8. So we have landed at this point. We need to read the 8 bytes. So star address to write this gives you the 8 bytes, and we need to add the delta. So after adding the delta, you will get the updated version, and we need to write this as at the same address to write. So we have successfully updated our base relocation. Okay, now there is only one thing left, that is getting to the entry point, that is optional header dot address of entry point. So you need to add the DLL base address plus entry point, that gives you the starting point of the code. And we are going to execute the DLL main. So we need to copy the DLL main syntax. So new DLL base plus optional header address of entry point. So this is the address we need to execute. So put on brackets and define the function pointer of the type DLL main. So it is very similar to what we are doing. So bool return type function pointer, pass in the parameters types h instance, d word, lp void, and put the brackets over this function pointer declaration, and now pass in the parameters. So pass in the null value for the h instance, and the second one is process attach, DLL process attach, and pass in null. So now we are executing the entry point. Now we can just return. So let's go and compile and see, and it has been successfully compiled. Now let's check if there are any bugs. So we are getting the kernel32.dll base address and getting the function addresses of load library, virtual alloc, get proc address, and virtual protect. And we have allocated the size of image space at the new dealer base address, and copying the contents from the old dealer base to the new dealer base, copying the headers, copying the sections. And now we are restructuring our pointers to the new dealer base, and then fixing base relocations, fixing imports. So that's all for this video about writing our own reflective loader. In the next video, we are going to write our injector to inject our DLL into the remote process. So in the previous video, we have written our reflective loader. In this video, we are going to write our injector. I have already written the injector function. It is very similar to what we have parsed the PE file. So I'm not going to write this again. I'm going to explain this. So we are going to declare a string DLL path, our reflective loader dot DLL, and we are reading the contents of the DLL, and this DLL can be read from the disk or downloaded from the URL. And here we are going to parse the PE from file, and we are getting the optional header pointer and retrieving the size of image. So the concept is the injector program will either read this DLL from the disk or download from the URL and allocate some memory inside the process and paste all the contents blindly and execute the test function. So this is the test function we have written. So this is the test function we have written where our reflective loader exists. So we are going to find the function RVA and add that to the loaded DLL base and execute the code at this test. So that is what I have done here. We have allocated the memory space of size of image with the page protection page execute read write, and we are writing the entire DLL contents in our own process and reading the exports and then finding the function RVA for the test function and then creating the thread at that point. So the test function gets executed and then we are waiting for the message box to close, wait for the thread to complete. So this code self injects the DLL. So when we go ahead and run this, you should see the message box and the test function and the function RVA 700. This is the raw offset. So the function RVA is 1300. So 1300 comes under the text section. So it is a 300 hexadecimal offset from virtual address. So that means if you add 300 to the raw address, you will get the 700. You can go and change this to hello there 2, hello there 2. We can compile the DLL, and you no need to compile the injector program again. It can inject the DLL and you can see the hello there 2. So we have successfully written our reflective loader. So if you go to system informer and go to the hulkbuster.exe, now you should see the RWX region. So there are two RWX regions. So you can see our DLL here, the code, and now you can see these two are similar. The sections, all the sections have the page protection RWX read write execute. In the next video, we are going to change the page protection for each and every section. So our loaded DLL will not look like a malicious because the RWX is a highly inspected region. So we can see now the text section is starting at the 1000. So this means this is the valid DLL file in the memory. If you go to the previous RWX, you can see the text section has already been started at 400. This is the raw file, raw contents, and this is the mapped contents. So we can even inject the DLL into the remote process. It is very similar. So I already have written the code. It is very similar. Once you read the contents of the PE file, and this the code for parsing the PE file I have written in a class, and this is a RAII function that gives you either a varied object or error value, and also it will clean up uh, all the memory in the destructor. So I'm going to give the code for this as well. So this is similar to the previous self injection. So we are going to open the process, put in the process ID virtual allocx, allocate memory in the remote process, write the contents of DLL, and then execute the code at this test function by the create remote thread. So you can build this one. So our notepad has been running. We can see the process ID of notepad 39316. So build the injector program again and run this, and you should see the hello there too message box being popped up. Now you can go to System Informer and Notepad. So you can search for RWX regions, and you can see there are two, and you can also see the remote base, the allocation remote base F44F0s. Okay, sorry, my bad. What we have done is we have freed this memory. So my bad, I'm looking for that memory region. Otherwise you can look for our newly allocated DLL, the RWX region. So this is ours. You can see it has been started at the 1000 virtual RVA. So that's how you can create an injector to inject our reflective loader DLL, and also our reflective loader has been working properly. In the next video we are going to see how to uh, apply the page protections for each section according to their section characteristics. So in this video we are going to apply page protections for each section according to the characteristics. You can see if you hover the mouse on the characteristics, you can see the bit flags, code, executable, readable. So this is RX, and you can see the next one is also only readable, and the next one is readable, writable, and next one is readable, and so on. So we are going to apply the page protections for each of these sections according to the characteristics, so that our DLL looks like a legitimate sections rather than entire RWX region. So let's go and do that. So first let's create a new variable old product is equals to 0, and we are going to fetch the section pointer because previously the section pointer has been updated. So copy this, paste here, change this to new DLL base. So we have got the section header updated to the starting section. So we are going to iterate through the section headers. Int I is equals to 0, I less than file header, number of sections I plus plus. In the end we are going to update the section header, increment this. So meanwhile we have to check the characteristics. If section header characteristics and do the end operation with the image scn section mem execute. So this is one. So make a brackets. So we are going to check if the section characteristics have the image scn mem execute. And copy this and do the end operation. And we are going to check for rwx. So change this to mem right and do the another end and check for read. So if the characteristics have the read write and execute flags have been set, then we are going to apply the page protection of page execute read write for this section. We have already found the virtual protect address, remember, from the array. So virtual protect, if you go to the documentation, you can see the first one is the address, base address, second one is the size and the new protections, and this will also store the old protection into a variable. So we are going to say we are going to cast this address as a function pointer of type boolean return type lp void size underscore t dword and pointer to dword. So this is a virtual protect address, and now we can pass in the parameters. The first one is the address, so the section header virtual address. So we need to add the new DLL base char star new DLL base plus virtual address comma the size is section header misc dot virtual size, and the next one is page protection page execute read write, and the last one is a pointer to the variable to store the old protection values. So this is for the first one. If the section is rwx, we can do else if. So copy all of this, paste here. Now we are going to do for rw. So remove the execute. So for rw, just copy this one and paste here and change this to page read write. So copy this and paste here, change this to rx. Page execute read, and then we are going to check for wx. So write execute means you need to apply the read write execute. So there is no write execute exclusively. If the characteristics are write execute, you are going to do the page execute read write, and the combinations have been completed rwx for 3 combinations, rw rx wx, and there comes our singular protection. If the section is only read, then we should page read only. Otherwise, if it is w, we can say page read write. If it is only executable, page execute. Otherwise, what we are going to do is we are going to apply page no access. So this applying page protections to each and every section has been completed. So notice the order we are doing. We should not do the first singular protections, because this matches this sorry, we did not change the read write execute. So if you put this if block in the top, there will be so many protections that matches this condition, like rwx also matches this because it contains write, and then we will be applying page read write, but in reality it should be read write execute. So that's why first we will process the uh, 3 combinations, then 2 combinations, and the single combination. So execute write read rwx, read write rw, rx page execute read, and write execute page execute read write, and read only and write and execute. Otherwise we have page no access. I think we are good to go. So let's go to our injector program, and we can open the notepad 21272, and we can see the message box, and also our uh, allocated memory has been freed, and the in the meantime respective loader allocated new memory address. So we can go to notepad, and we need to search for rwx, not rwx but some region with that looks like legitimate protection. It's 36 kb. I think this can be our allocated DLL. So the first section, the text section, so you can see the contents here. So this is our indeed our uh, memory region that was allocated by our reflective loader DLL. So now you can see uh, even the starting headers contain rwx, the remaining sections have the appropriate page protections. So the text section contains rx, and the remaining read only read. So in this way you can make it look like a legitimate, than the complete RWX page protection. So in this video we are going to see an intrinsic function return address. So in the C++ 64-bit MSVC compiler, you cannot use the inline assembly, but in Rust you can do that. In C++ there is no option. So if you have an inline assembly option in the Rust, so you can actually load the current RIP register address, but here we need to use an intrinsic return address. So this gets you the current executing address value. So what we can do is we can just simply copy this and paste here. I have already pasted this. So instead of returning the void here, do the void star, and instead of DLL main we can do the get return address. So this is very similar. So after we have used the get return address, it will use this intrinsic function to get the current execution address value. From there onwards we can we can backtrack for the MZ value. So let's quickly check this if this works or not. Let's build our DLL, and the notepad has been running 42004. And we can see we have got the message box. So you can use the DLL main as well, as long as the DLL main exists. Otherwise you can use this position independent get return address. So that's all for this course. In this course we have learned about how to write the position independent reflective loader that loads the entire PE file in the new memory space and copies the headers sections, and then fixes the imports base relocations and execute the code at the address of entry point. So that's all for this course. All the code will be available in the description. I will provide a GitHub my GitHub repo link. Thank you.